In the cold darkness between stars, two objects have appeared in our solar system that defy comfortable explanation. The first arrived in 2017, tumbling through space on an impossible trajectory from beyond our sun's gravitational reach. They called it ʻOumuamua, messenger from afar arriving first. Its elongated shape, mysterious acceleration, and 11-day disappearance left astronomers with more questions than answers. For nearly 8 years, it remained unique, a solitary visitor from the cosmic void. Then, in 2025, our telescopes detected something larger approaching, something following a path that should occur by chance only once in several hundred attempts. We have always assumed that interstellar space was empty, that visitors from other star systems would be random debris scattered by cosmic accidents. But what if we were wrong? What if these objects represent something far more deliberate, a reconnaissance mission conducted by intelligences we have never imagined? Before we venture deeper into this cosmic mystery, take a moment to like this video and subscribe to my channel if you too find yourself drawn to these stellar questions. And I'd love to hear from you in the comments. Tell me where you're listening from and what time it is for you right now. It's incredible to know that people across the globe are pondering these same mysteries alongside us. Tonight, we explore the possibility that ʻOumuamua was only the scout, and that what follows may be the mothership. We will examine orbital mechanics that suggest intention rather than accident, investigate the dark forest theory of cosmic civilizations, and consider why advanced beings might choose to observe us from a distance before making contact. Get comfortable. Let your mind drift among the stars. Our journey into the unknown begins now. On the 19th of October 2017, astronomers at the Pan-STARRS 1 telescope in Hawaii made a discovery that would change our understanding of interstellar space. They detected an object unlike anything seen before, tumbling through our solar system on a trajectory that could only mean one thing. It had come from the stars themselves. They named it ʻOumuamua, a Hawaiian word meaning messenger from afar arriving first. This elongated reddish object became the first confirmed interstellar visitor to our solar system. Its discovery was groundbreaking, but also frustrating. By the time astronomers realized what they were looking at, ʻOumuamua was already racing away from the sun, visible for only 11 precious days before fading into the cosmic dark. It left behind more questions than answers, its brief visit sparking debates that continue to this day. For nearly 8 years, ʻOumuamua remained unique, a solitary ambassador from the void between stars. Scientists estimated that such interstellar visitors might arrive only once every few million years, making its discovery a stroke of extraordinary luck. We settled into the assumption that we might never see another in our lifetimes. Then, on the 1st of July 2025, the Atlas telescope system in Chile detected something remarkable. Another interstellar object was approaching, following a hyperbolic trajectory that marked it as definitely originating from beyond our solar system. Designated 3I, Atlas, this new visitor would become only the third confirmed interstellar object ever discovered. The timing was startling. After tens of millions of years of apparent emptiness, 2 interstellar objects had arrived within less than a decade of each other. The statistical improbability of such timing began to spark questions that reached far beyond astronomy into the realm of speculation and wonder. What if these visits weren't random at all? What if ʻOumuamua hadn't been a lone wanderer, but something more purposeful? What if it had been a scout, sent ahead to gather information about our solar system? And if that were true, what would 3I, Atlas, represent? A response to whatever ʻOumuamua had discovered? A follow-up mission based on the first visitor's reconnaissance? These questions lead us into one of science fiction's most chilling concepts, the dark forest theory. Proposed in Lou Cixin's three-body problem series, This theory suggests that the universe might be filled with intelligent civilizations, all remaining silent and hidden because revealing oneself could mean annihilation. In such a cosmos, any contact between civilizations would be cautious, methodical, perhaps beginning with stealthy scouts designed to gather information before any overt contact is attempted. Tonight, as you settle into rest, we'll explore this possibility together. We'll journey through the facts we know about these mysterious visitors, examine the evidence with both scientific rigor and imaginative wonder, and consider what it might mean if we're not looking at random cosmic debris, but at something far more intentional. This is not a story of unfounded conspiracy theories or wild speculation. Instead, it's an exploration of the boundary between known science and informed imagination, a gentle investigation into one of the most intriguing mysteries of our time. We'll present the facts as they stand, acknowledge the uncertainties, and allow ourselves to wonder about possibilities that, while unproven, are not impossible. Our journey will take us from the technical details of orbital mechanics to the philosophical implications of contact with intelligence from beyond our world. We'll examine the arguments both for and against the Scout hypothesis, explore alternative explanations, and consider what future observations might reveal. But for now, as the night deepens and your mind begins to settle, let yourself drift into contemplation of the vast cosmos above. Somewhere out there, 3i, Atlas continues its journey through our solar system, carrying with it secrets that may take decades to unravel. Whether it's a simple chunk of ancient ice and rock or something more profound, its presence reminds us that the universe is far stranger and more wonderful than we often imagine. The stars are calling, and tonight we listen. Part 2. ʻOumuamua, the First Messenger. It was a routine night of sky surveying when Dr. Robert Werrick first noticed the unusual object in images captured by the Pan Stars 1 telescope. Located on the summit of Haleakala in Hawaii, this powerful instrument was designed to scan the heavens for potentially hazardous asteroids, cataloguing the countless chunks of rock and ice that populate our solar system. But on the 19th of October, 2017, it found something unprecedented. The object appeared as nothing more than a faint dot of light moving against the star field in a way that immediately caught Werrick's attention. Its motion was wrong, too fast, and following a path that didn't match any known asteroid or comet orbit. When astronomers calculated its trajectory, they discovered something remarkable. This visitor was following a hyperbolic path, meaning it had arrived from interstellar space and would continue on, never to return. They named it 1i, ʻOumuamua, with the 1i designation marking it as the first confirmed interstellar object, and ʻOumuamua chosen for its meaning in Hawaiian. A messenger from afar arriving first. The name proved more prophetic than anyone could have imagined. As observations accumulated, ʻOumuamua revealed characteristics that defied easy explanation. Most striking was its shape, inferred from the dramatic changes in brightness as it tumbled through space. The light curve suggested an extremely elongated object, possibly 10 times longer than it was wide, resembling a cosmic cigar or needle rather than the roughly spherical shape typical of asteroids and comets. Its color was distinctly reddish, similar to objects found in the outer reaches of our own solar system, suggesting a surface darkened and altered by eons of exposure to cosmic radiation. This coloration hinted at an ancient origin, an object that had been wandering the galaxy for millions or even billions of years before its chance encounter with our Sunday. But perhaps most puzzling was what ʻOumuamua didn't show. Despite its trajectory bringing it closer to the Sun than Mercury's orbit, it displayed no visible coma or tail, the hallmarks of a typical comet. Comets develop these features when solar heating causes their icy components to sublimate, creating the beautiful tales that have inspired human imagination for millennia. ʻOumuamua remained stubbornly tailless, leading astronomers to initially classify it as an asteroid despite its interstellar origin. Yet, as precise measurements of its trajectory continued, another mystery emerged. ʻOumuamua was accelerating slightly as it moved away from the Sun, a deviation that couldn't be explained by solar gravity alone. This acceleration was tiny but measurable, and it sparked intense debate among scientists. Some proposed outgassing, invisible jets of material being ejected from the object's surface as it was heated by the sunday. Others suggested radiation pressure from sunlight itself might be affecting such an elongated, possibly flat object. Dr. Avi Loeb, a respected astronomer at Harvard University, proposed a more speculative explanation. What if Oumuamua wasn't a natural object at all? What if its unusual shape and acceleration could be explained if it were an artificial construct, perhaps a solar sail created by an intelligent civilization? His suggestion that Oumuamua might represent our first contact with alien technology was met with both fascination and skepticism from the scientific community. The debate over Oumuamua's nature was complicated by time. Unlike asteroids and comets that orbit the Sun repeatedly, allowing for extended study, this interstellar visitor was here and gone in the cosmic equivalent of an instant. High-quality observations were possible for only 11 days before the object became too faint for detailed study, racing away from our solar system at more than 40 kilometers per second. By the time astronomers fully understood what they were observing, it was too late to dispatch a spacecraft for a closer look. Oumuamua faded into the darkness of interstellar space, leaving behind a wealth of data but an equal measure of mystery. No probe would ever touch its surface, no detailed images would reveal its true shape, no instruments would directly analyze its composition. In those brief 11 days, Oumuamua had delivered a message that fundamentally changed our understanding of our cosmic neighborhood. It demonstrated that objects from other star systems do occasionally visit ours, that interstellar space isn't the empty void we once imagined, and that the galaxy might be full of wanderers carrying stories from distant shores. But what story did Oumuamua carry? Was it simply a fragment blasted from some distant world by an ancient collision, set tumbling through the galaxy by chance? Was it the remnant of a shattered comet from another star system, its icy components long since lost to the vacuum of space? Or could it have been something more purposeful, a probe sent by intelligent beings to study our solar system from a safe distance? The messenger had arrived, delivered its cryptic message, and departed, leaving us to wonder about its origins and purpose. In the years that followed, Oumuamua became a symbol of both discovery and frustration, proof that the universe still holds surprises while reminding us of the limits of our current technology and understanding. As we drift deeper into contemplation, consider the remarkable journey that brought Oumuamua to our solar system. For millions of years, it travelled through the cold emptiness between stars, a solitary traveller in the cosmic dark. What forces shaped its unusual form? What distant star system did it call home? And perhaps, most intriguingly, if it was indeed a scout sent by an intelligent civilization, what did it observe during its brief passage through our neighbourhood? The answers to these questions remain locked in the depths of space, carried away by our enigmatic first interstellar visitor. But Oumuamua's story was just the beginning, and its true significance may only become clear in light of what followed. Part 3. Introducing 3I, Atlas, the third interstellar visitor. The morning of the 1st of July, 2025, began like countless others at the Atlas Observatory in Chile. The Asteroid Terrestrial Impact Last Alert System had been diligently scanning the southern skies, part of a global network designed to detect potentially hazardous objects that might threaten Earth. But as astronomers reviewed the night's data, they found something that would rewrite our understanding of interstellar visitors once again. Hidden among the routine asteroid detections was an object that didn't belong. Its motion was too fast, its trajectory too steep, following a path that could only mean one thing. This was another visitor from beyond our solar system. After careful analysis and confirmation observations, the object received the designation 3I, Atlas, marking it as the third confirmed interstellar object in human history. The discovery sent ripples of excitement through the astronomical community. After nearly 8 years since ʻOumuamua's brief visit, many had wondered if we would ever see another interstellar traveler in our lifetimes. The statistical models suggested such objects might arrive only once every few million years, making ʻOumuamua's discovery a stroke of extraordinary fortune. Yet here was another, arriving less than a decade later. Initial size estimates for 3I, Atlas placed it somewhere between 0.32 and 5.6 kilometers across, making it significantly larger than its predecessor. Where ʻOumuamua had been perhaps a few hundred meters in length, 3I, Atlas was a substantial body, large enough to be seen clearly by ground-based telescopes and space-based observatories alike. Unlike its predecessor, 3I, Atlas immediately began displaying the behavior of a typical comet. As it approached the inner solar system, solar heating began to sublimate ices within its structure, creating a visible coma and tail. The Hubble Space Telescope captured stunning images of gas and dust streaming away from the object, confirming the presence of water vapor and other familiar cometary materials. The Swift Space Telescope, originally designed to study gamma-ray bursts, was quickly redirected to observe the new visitor. Its ultraviolet observations revealed clear evidence of water vapor outgassing, dispelling any immediate mystery about the object's basic nature. Here was a comet, albeit one that had spent eons wandering the galaxy before arriving at our doorstep. But as astronomers plotted 3I, Atlas's trajectory more precisely, intriguing details began to emerge. The object's path through our solar system would bring it closest to the Sun on the 29th of October, 2025, following an orbital plane that aligned remarkably closely with the ecliptic, the disk-like region where most planets orbit our star. This alignment was puzzling. Random objects arriving from interstellar space should approach from any direction, their orbital planes distributed more or less evenly around the celestial sphere. The probability of an interstellar visitor naturally aligning so closely with the ecliptic plane was quite low, leading some astronomers to wonder if this alignment might be more than coincidental. Dr. R.V. Loeb, still advocating for serious consideration of artificial explanations for unusual interstellar objects, published a paper suggesting that 3I, Atlas's trajectory, might be deliberately chosen. If one wanted to conduct a survey of multiple planets in our solar system, he argued, following the ecliptic plane would be the most efficient route, like taking a cosmic highway that passes by all the major destinations. Analysis of 3I, Atlas's origin, suggested it had come from the thick disk of our galaxy, a region populated by stars between 7 and 14 billion years old. This ancient stellar neighborhood implied that the object had been wandering space for an extraordinarily long time, possibly since the early epochs of galactic formation. The international astronomical community mobilized to study this rare visitor. The James Webb Space Telescope turned its powerful infrared eyes toward 3I, Atlas, seeking to understand its composition and structure in unprecedented detail. Ground-based observatories around the world coordinated observation campaigns, ensuring continuous coverage as the object approached the inner solar system. Perhaps most ambitiously, mission planners began considering whether NASA's Juno spacecraft, currently orbiting Jupiter, might be able to conduct a flyby of 3I, Atlas. Such a maneuver would require precise timing and trajectory adjustments, but it offered the tantalizing possibility of humanity's first close-up look at an interstellar object. The public reaction to 3I, Atlas's discovery, was immediate and intense. Social media buzzed with speculation about the object's nature and origins. The timing of its arrival, so soon after ʻOumuamua, struck many as suspicious. Could these visits really be coincidental, or was something more deliberate at work? Science fiction fans immediately began drawing connections between the two objects, imagining scenarios where ʻOumuamua had been an advanced scout, gathering information about our solar system and transmitting it back to some distant civilization. In this speculative narrative, 3I, Atlas, might represent the response to that reconnaissance, a larger object sent to follow up on whatever the first visitor had discovered. The mainstream scientific community remained cautious about such interpretations, emphasizing that 3I, Atlas, displayed all the expected characteristics of a natural comet. Its water vapor emissions, dust production, and overall behavior matched theoretical models for how an ancient interstellar comet should behave when heated by our Sunday, yet the questions persisted. Why 2 interstellar visitors in less than a decade? Why did 3I, Atlas, follow such a convenient trajectory through the heart of our solar system? And perhaps most intriguingly, could there be aspects of this object that our current instruments simply couldn't detect? As 3I, Atlas continued its approach toward perihelion, astronomers prepared for the most comprehensive study of an interstellar object ever attempted. Every telescope capable of observing it was enlisted, every analytical technique was brought to bear. If this visitor held secrets beyond its apparent nature as an ancient comet, the astronomical community was determined to find them. But as the object grew brighter and its coma expanded, another possibility began to crystallize in the minds of those willing to entertain extraordinary explanations. What if the comet-like activity was exactly what it appeared to be, but not the whole story? What if, within that cloud of gas and dust, shielded from our instruments by the very material it was shedding, something else entirely was making its way through our solar system? The third interstellar visitor had arrived, and with it came questions that would challenge our understanding of both our cosmic neighborhood and our place within it. As we prepare to explore these possibilities further, let your mind drift into the vast darkness between stars, imagining the ancient journey that brought this mysterious object to our solar system, and wondering what secrets it might carry within its icy depths. Part 4. The Dark Forest Theory: Silence, Surveillance, and Survival. In the quiet hours before dawn, when the night sky reveals its deepest secrets, it's natural to wonder, where is everybody? The universe contains hundreds of billions of galaxies, each filled with hundreds of billions of stars, many of which likely harbour planetary systems. The sheer numbers suggest that life, even intelligent life, should be common. Yet when we listen to the cosmos with our most sensitive instruments, we hear only silence. This contradiction, known as the Fermi paradox, has puzzled scientists and philosophers for decades. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" During a casual conversation about UFOs in 1950, the paradox highlights the apparent contradiction between the high probability of extraterrestrial life and our lack of contact with it. Many solutions have been proposed to explain this cosmic quiet. Perhaps intelligent life is extraordinarily rare. Perhaps civilizations typically destroy themselves before they can spread beyond their home worlds. Perhaps the distances between stars are simply too vast for meaningful contact. Or perhaps there's something more unsettling at work. In his acclaimed three-body problem trilogy, author Liu Cixin proposed one of the most chilling possible explanations, the dark forest theory. Named after the second book in the series, this concept suggests that the universe is indeed filled with intelligent civilizations, but they all remain hidden because revelation means destruction. The theory rests on several assumptions about the nature of cosmic civilizations. First, that survival is the primary goal of any civilization. Second, that civilizations have no way to determine whether other civilizations will be hostile or peaceful. And third, that technological advancement tends to accelerate, meaning a civilization that seems primitive today might become a galactic superpower tomorrow. In such a universe, the discovery of another civilization presents an existential dilemma. You cannot know their intentions, cannot predict their future capabilities, and cannot be certain they won't eventually pose a threat to your survival. The safest course, therefore, is to destroy them before they can threaten you. This creates a cosmic environment resembling a dark forest at night, where every civilization is an armed hunter moving carefully through the trees. They must remain completely silent and invisible, because the slightest sound, the faintest light, might attract the attention of other hunters who will eliminate them without hesitation. In Liu's fictional universe, this theory explains the Great Silence. Civilizations exist, but they dare not reveal themselves. Any signal broadcast into space is essentially a suicide note, announcing your location to potential destroyers. The cosmos becomes a place of terrible loneliness, where countless intelligent species exist in isolation, each terrified of making contact with the others. While this remains a work of fiction, the dark forest theory has gained serious consideration among some scientists and philosophers studying the Fermi paradox. It offers an explanation for why SETI efforts have found no clear evidence of alien technology, why we see no obvious signs of galactic engineering projects, and why the universe appears so remarkably quiet despite its apparent potential for life. But how might such a universe handle the need for information gathering? Even the most paranoid civilization would need to understand what lies beyond their own star system. They might develop colonies, explore nearby worlds, or search for resources and potential threats. Yet, direct contact would be far too dangerous. The solution, in a dark forest universe, would be surveillance from a distance. Probes might be dispatched to study other star systems, but these scouts would need to remain undetected. They might disguise themselves as natural objects, move slowly to avoid attention, and gather information without revealing their artificial nature. Such probes would need to be extraordinarily sophisticated, capable of autonomous decision-making across the vast distances and time delays of interstellar communication. They might observe a target system for years or centuries, cataloguing its planets, studying any signs of life or technology, and transmitting their findings back to their creators. Consider how such a strategy might work in practice. A civilization discovers a star system that appears to harbor life. Rather than making direct contact or sending obvious artificial probes, they launch objects designed to appear natural. These scouts approach the system on trajectories that mimic interstellar debris, perhaps even disguising their propulsion systems or artificial components. The first probe conducts a preliminary survey, gathering basic information about the system's layout, the presence of planets, and any signs of technological development. It then transmits this data back to its origin, a process that might take years or decades depending on the distances involved. If the survey reveals something interesting or concerning, a follow-up mission might be dispatched. This second probe could be larger, more sophisticated, capable of conducting more detailed observations, or even preparing for future contact or intervention. From our perspective on Earth, such probes might be nearly indistinguishable from natural interstellar objects. They would follow ballistic trajectories, show appropriate signs of age and cosmic ray exposure, and avoid any obvious artificial behaviors that might reveal their true nature. This framework provides a chilling context for considering objects like ʻOumuamua, and 3I, Atlas. What if Oumuamua wasn't a random chunk of interstellar debris, but a carefully disguised scout probe? What if its unusual characteristics, its strange acceleration, its mysterious elongated shape, were not natural anomalies, but artificial features designed for specific purposes? And what if 3I, Atlas, represents the response to whatever Oumuamua discovered during its brief passage through our solar system? A larger, more capable probe dispatched to conduct follow-up observations based on the initial scout's report? The timeline fits this speculative scenario disturbingly well. Oumuamua arrived in 2017, spent 11 days observing our solar system, and departed. If it transmitted its findings back to its origin at the speed of light, and if that origin was relatively nearby in galactic terms, a response could have been launched years ago, timed to arrive precisely when 3I, Atlas, was discovered. Of course, this remains purely speculative. The dark forest theory is a work of science fiction, and there are many more conventional explanations for both the Fermi paradox and the characteristics of our interstellar visitors. But it provides a framework for understanding why extraterrestrial intelligence might choose to remain hidden, and how they might conduct surveillance of other star systems without revealing themselves. As you contemplate these possibilities, consider the profound implications they would have for humanity's future. If we live in a dark forest universe, our own broadcasts into space, our increasingly obvious technological signatures, might already have marked us for observation or worse. The very act of searching for extraterrestrial intelligence might be the most dangerous thing our species has ever attempted. Yet perhaps there's comfort in another possibility. Maybe civilizations in the cosmic dark forest eventually learn to trust, to cooperate, to move beyond the terrible logic of preemptive destruction. Maybe first contact, when it comes, will be gentle and gradual, conducted by patient observers who have watched us for years and concluded that we pose no threat. In the meantime, we continue to listen to the silence, to watch for visitors in the night, and to wonder whether the next interstellar object to pass through our solar system might carry with it answers to questions we're only beginning to learn how to ask. Part 5. Anomalies around 3I, Atlas. Unlikely course, unsettling hypotheses. As astronomers around the world continued to study 3I, Atlas throughout the summer and autumn of 2025, subtle details about its behavior began to accumulate into a picture that was both familiar and strange. On the surface, it appeared to be exactly what most scientists expected, an ancient comet from interstellar space, behaving precisely as theoretical models predicted. Yet beneath this comfortable explanation, several anomalies lingered, waiting to be either resolved or acknowledged as genuinely mysterious. The most striking anomaly remained its trajectory. Dr. Avi Loeb, who had previously suggested that Oumuamua might be an artificial object, turned his attention to the mathematical improbability of 3I, Atlas's orbital alignment. In a paper that sparked intense debate within the astronomical community, he calculated that the odds of a random interstellar object arriving on a trajectory so closely aligned with our solar system's ecliptic plane were approximately 1 in several hundred. To understand why this matters, imagine our solar system as a flat disk, with the Sun at the center and the planets orbiting in roughly the same plane. This disk, called the ecliptic plane, contains most of the interesting features of our cosmic neighborhood: the rocky inner planets, the gas giants, the asteroid belt, and the regions where Earth-crossing comets typically travel. An object arriving from a random direction in space should be equally likely to approach from any angle relative to this disk. It might come from above, below, or at any intermediate inclination. The fact that 3I, Atlas, arrived almost precisely aligned with the ecliptic meant it would pass relatively close to multiple planets during its journey through the inner solar system. Loeb argued that if one wanted to conduct an efficient survey of our solar system, following the ecliptic plane would be the obvious choice. Like a cosmic highway system, it would allow a probe to gather information about Earth, Mars, Jupiter, and the other major bodies with minimal energy expenditure. The trajectory that made 3I, Atlas, appear suspicious also made it remarkably convenient for observation purposes. Critics of this interpretation pointed out that unlikely events happen all the time in astronomy. The universe is vast and filled with countless objects moving in every conceivable direction. With enough observations, even highly improbable events become not only possible but inevitable. Perhaps 3I, Atlas, was simply the exception that proved the rule, the one in several hundred chance that happened to occur during the brief window of human astronomical capability. Yet, the timing continued to bother many observers. 2 interstellar objects in less than a decade, after what appeared to be millions of years of absence. If these visits were truly random, the clustering in time seemed almost as improbable as the orbital alignment. It was as if someone had waited until humanity developed the technology to detect such objects before dispatching them. The observations from various space telescopes added both clarity and confusion to the picture. The James Webb Space Telescope's infrared instruments revealed the detailed composition of 3I, Atlas's coma, confirming the presence of water vapor, carbon dioxide, and other molecules expected from sublimating ice. These findings strongly supported the natural comet hypothesis, showing that the object contained exactly the materials that should be present in a chunk of primordial ice and rock. But some researchers began to wonder whether this cometary activity might serve multiple purposes. The gas and dust streaming from 3I, Atlas created a natural camouflage, surrounding the object's nucleus with a cloud of material that would effectively hide any smaller structures from our instruments. If something artificial were embedded within or attached to the comet's core, the active coma would make it virtually undetectable from Earth. The Hubble Space Telescope's high-resolution images showed the expected nucleus at the center of the coma, appearing as little more than a bright point of light surrounded by the characteristic fuzzy envelope of outgassing material. Ground-based telescopes equipped with adaptive optics could resolve some structure in the coma itself, but the central body remained essentially a mystery, its true shape and surface features hidden behind the veil of its own activity. Radio telescopes around the world turned their attention to 3I, Atlas, listening for any artificial signals that might emanate from the object. The search covered a wide range of frequencies, from the waterline at 21 centimeters to higher frequencies that might be used for interstellar communication. So far, these efforts had detected only the natural radio emissions expected from the object's interaction with the solar wind, but the search continued as the object approached perihelion. Perhaps most intriguingly, mission planners at NASA and ESA began seriously considering whether the Juno spacecraft, currently in orbit around Jupiter, could be maneuvered to intercept 3I, Atlas, during its passage through the outer solar system. Such a mission would require precise timing and careful use of Jupiter's gravity to boost Juno onto an intercept trajectory. The proposed flyby would use the Oberth effect, gaining energy by firing Juno's engines while deep in Jupiter's gravitational well. This technique could potentially provide enough velocity to match 3I, Atlas's trajectory, allowing humanity's first close-up look at an interstellar object. The flyby would last only minutes, but in that brief time, Juno's instruments could gather more detailed information about the object than years of ground-based observation. The engineering challenges were substantial. Juno had been designed to study Jupiter, not to intercept high-speed objects in the outer solar system. Its instruments would need to be recalibrated for the encounter, its navigation systems updated for an unprecedented type of mission. The timing window was narrow, requiring a decision within months and execution within a year. Yet the scientific value of such a mission was undeniable. Direct measurements of 3I, Atlas's composition, magnetic field, and internal structure could definitively answer questions about its nature. High-resolution images of its nucleus could reveal whether it was a simple chunk of ice and rock or something more complex. Meanwhile, amateur astronomers and citizen scientists around the world contributed their own observations to the growing database. Advanced amateur telescopes, equipped with sensitive CCD cameras, could track the object's brightness variations and help refine understanding of its rotation period and shape. These grassroots efforts complemented the professional observations, creating a global network of eyes watching our interstellar visitor. As winter approached in the northern hemisphere, 3I, Atlas continued to brighten as it neared the Sunday. Its coma expanded, its tail grew more prominent, and its behavior remained consistently comet-like. Yet the questions persisted, fueled by the statistical improbabilities and the haunting precedent of ʻOumuamua. Some astronomers began to consider hybrid scenarios that might reconcile the natural observations with the unusual circumstances. Perhaps 3I, Atlas was indeed a natural comet, but one that had been deliberately selected and redirected by an intelligent civilization. Ancient spacefaring cultures might have developed techniques for moving asteroids and comets, using them as camouflaged probes for studying other star systems. Such a scenario would explain both the object's natural composition and its suspicious trajectory. A real comet, nudged onto a specific path millions of years ago, would behave exactly like 3I, Atlas, was behaving. The artificial element would be invisible to our instruments, hidden in the selection and timing of an otherwise natural object. As you drift into deeper contemplation, consider the delicate balance between skepticism and wonder that defines our approach to these cosmic mysteries. The universe is indeed stranger than we imagine, filled with phenomena that challenge our understanding and push the boundaries of the possible. Yet it's also governed by consistent physical laws that make certain explanations more likely than others. Whether 3I, Atlas, is a simple interstellar comet or something more profound, its presence in our solar system represents a remarkable opportunity for discovery. Each observation, each measurement, each careful analysis brings us closer to understanding not just this particular object, but the nature of interstellar space itself and our place within the cosmic community. The anomalies remain, waiting for resolution. The questions persist, demanding answers. And somewhere in the darkness beyond our solar system, other travelers may already be making their way toward us, carrying their own mysteries and revelations across the vast emptiness between the stars. Part 6. Connecting the dots. Could 3I, Atlas, be the mothership? As autumn deepened and 3I, Atlas approached its closest point to the sun, a speculative narrative began to crystallize among those willing to entertain extraordinary possibilities. The pieces seemed to fit together with an unsettling elegance. First a small, enigmatic scout, then a larger follow-up mission arriving with curious precision. Could these two interstellar visitors represent the opening moves in humanity's first contact with an alien intelligence? The concept of a mothership has deep roots in both aerospace engineering and science fiction. In human space exploration, we've long understood the value of large, capable platforms that can support multiple missions. The International Space Station serves as a mothership for scientific experiments and crew operations. Aircraft carriers function as mobile bases for smaller, specialized craft. Even in our early interplanetary missions, we've used this model. Cassini carried the Huygens probe to Saturn, and various Mars missions have deployed rovers and landers from orbiting platforms. The advantages of this approach are clear. A mothership can carry more sophisticated equipment, maintain better communications with home base, and support extended operations in ways that smaller probes cannot. For an interstellar mission crossing the vast emptiness between stars, such capabilities would be invaluable. Consider the challenges facing any civilization attempting to study a distant star system. The journey time alone would be measured in millennia or longer, depending on the propulsion technology available. Any probe making such a journey would need to be remarkably self-sufficient, capable of operating for thousands of years without maintenance or direct control from its creators. A scout probe like ʻOumuamua could serve as an advanced reconnaissance mission, gathering basic information about the target system and transmitting it back to the mothership following behind. This two-stage approach would allow for adaptive mission planning. If the scout discovered something particularly interesting or concerning, the mothership could adjust its approach accordingly. The timeline fits this speculative scenario with disturbing precision. ʻOumuamua arrived in 2017, spent 11 days conducting what could be interpreted as a systematic survey of our inner solar system, then departed on a trajectory that would carry it back toward interstellar space. If it were equipped with communication systems, it could have transmitted its findings to a following mothership at any point during or after its visit. Even at the speed of light, interstellar communication takes years. But if 3I, Atlas, had been launched from a relatively nearby system, perhaps 10 to 20 light-years away, the timing works out remarkably well. A signal sent by ʻOumuamua in 2017 could have reached the mothership while it was still in the outer reaches of its journey toward our system, allowing for course corrections or mission updates. From this perspective, 3I, Atlas's trajectory through the ecliptic plane, takes on new significance. Rather than being a statistical anomaly, it could represent a deliberate choice to maximize observation opportunities. By following the plane where our planets orbit, the mothership could conduct close-range surveys of multiple worlds with minimal energy expenditure. The size difference between the two objects also supports this interpretation. Where ʻOumuamua was relatively small, perhaps a few hundred meters in length, 3I, Atlas measures several kilometers across. This scale difference mirrors the relationship between reconnaissance drones and the larger platforms that deploy them in human military and scientific operations. But if 3I, Atlas, is indeed a mothership, what might it be carrying within its disguise of ice and rock? The possibilities are as fascinating as they are speculative. Advanced sensor arrays could be embedded within the comet's nucleus, protected by layers of natural material and camouflaged by the object's cometary activity. The outgassing that creates its coma and tail might serve a dual purpose, appearing natural while also providing a convenient exhaust system for internal operations. Communication equipment could be hidden within the object's core, transmitting data back to its origin using frequencies and modulation schemes that our current technology cannot detect or interpret. Power systems might draw energy from the temperature differential between the object's sun-heated surface and its cold interior, or from more exotic sources that leave no detectable signature. Most intriguingly, the mothership might carry smaller probes of its own, ready to be deployed at strategic points during its passage through our solar system. These subprobes could be released during perihelion, when the increased cometary activity would mask their departure. They might then use gravitational assists from the planets to reach specific targets: Earth's moon, the asteroid belt, or the outer planets themselves. The behavioral evidence, while circumstantial, is consistent with this interpretation. 3I, Atlas, has maintained a steady approach toward the inner solar system, neither accelerating unexpectedly like ʻOumuamua, nor deviating from its predicted path. This could indicate a more sophisticated propulsion system, one capable of making subtle adjustments without creating detectable signatures. The object's rotation period and brightness variations suggest a roughly spherical or slightly elongated shape, quite different from Oumuamua's extreme aspect ratio. This more conventional geometry would be consistent with a designed object that needs to maintain structural integrity while carrying complex internal systems. Radio telescope observations have so far detected no artificial signals from 3I, Atlas, but this absence of evidence isn't evidence of absence. An advanced civilization would likely use communication methods far beyond our current understanding. They might employ quantum entanglement for instantaneous communication, directional laser communications that don't spill over for us to detect, or modulation schemes embedded within natural phenomena that appear to be simple thermal emissions. The proposed Juno flyby mission takes on special significance in this context. If 3I, Atlas, is indeed a mothership, close-range observations might reveal details that ground-based telescopes cannot detect. Juno's magnetometer could detect artificial magnetic fields generated by internal systems. Its radiation detectors might register emissions from exotic power sources. High-resolution images could reveal surface features inconsistent with a natural comet. But such a close encounter would also represent a moment of significant risk. If the object is indeed an alien mothership, its operators would certainly be aware of the approaching spacecraft. The flyby could be interpreted as either a peaceful scientific gesture or a potential threat, with consequences that might ripple far beyond the immediate encounter. Some researchers have suggested that humanity's response to these possible visitors should be carefully considered. If we are indeed being observed by an advanced civilization, our actions during this critical period might determine the nature of future contact. Aggressive or fearful responses could be interpreted as hostile intent, while open scientific inquiry might signal our readiness for peaceful interaction. The mothership hypothesis also raises profound questions about the observer's intentions. Why reveal themselves now in this indirect manner? Why not make open contact if their purposes are benign? The answer might lie in the vast differences between civilizations separated by millions of years of evolution and technological development. An ancient spacefaring species might view humanity much as we view a newly discovered tribe in a remote jungle. Interesting, potentially significant, but requiring careful study before any direct contact. They might be waiting to see how we develop, how we handle the knowledge of their presence, how we respond to the implications of not being alone in the universe. Alternatively, their caution might stem from bitter experience with first contact scenarios in their own past. They might have learned, through tragedy or near disaster, that premature contact between civilizations of vastly different capabilities can lead to the destruction of the less advanced culture. Their gradual approach might represent a carefully developed protocol for minimizing such risks. The cometary disguise itself suggests a sophisticated understanding of both human psychology and observational capabilities. By appearing as natural objects, these visitors avoid triggering the fear and paranoia that might accompany obvious alien spacecraft. They can conduct their observations while allowing humanity time to adjust to their presence gradually. Yet the disguise isn't perfect, as evidenced by the growing speculation about their true nature. Perhaps this is intentional, a way of slowly acclimatizing us to the possibility of contact while maintaining plausible deniability for those not ready to accept such a reality. As 3I, Atlas continues its journey through our solar system, the mothership hypothesis remains unproven but tantalizingly plausible. Every new observation, every spectroscopic analysis, every measurement of its trajectory adds another piece to the puzzle. Whether that puzzle ultimately reveals a natural interstellar comet or something far more extraordinary remains to be seen. In the quiet hours of the night, as you contemplate these possibilities, consider the profound implications of living in a universe where intelligence has learned to travel between the stars. Whether as scouts and motherships, as ancient wanderers, or as something else entirely, these interstellar visitors remind us that the cosmos is far more dynamic and interconnected than we once imagined. The dots are there to be connected, the patterns waiting to be recognized. Whether they spell out a message of contact, coincidence, or something else entirely, may depend as much on our readiness to see the truth as on the nature of the truth itself. Part 7. Technical Insights. The Physics of Interstellar Interlopers. To truly understand the significance of our interstellar visitors, we must delve into the elegant mathematics and physical principles that govern their motion through space. The technical details, while sometimes complex, reveal the profound challenges involved in detecting, studying, and potentially intercepting these cosmic wanderers. The fundamental difference between interstellar objects and the familiar bodies of our solar system lies in their orbital characteristics. Every asteroid, comet, and planet in our solar system follows an elliptical orbit around the Sun, bound by gravity in eternal dance. Even the most eccentric comets, those with the longest and most stretched orbits, are gravitationally tied to our star and will eventually return. Interstellar objects follow hyperbolic trajectories, mathematical curves that never close back on themselves. These paths represent unbound orbits, where the object's velocity exceeds the escape velocity needed to break free from the Sun's gravitational influence. Like a stone thrown too hard to fall back to Earth, these visitors arrive with enough speed to pass through our solar system once and continue into the cosmic deep. The shape of these hyperbolic orbits reveals crucial information about the object's origins and destinations. By working backward from observed positions, astronomers can calculate where these visitors came from in the galaxy, tracing their paths through space for millions of years. Similarly, by projecting forward, we can determine where they're headed after leaving our solar system. For ʻOumuamua, this analysis suggested an origin from the direction of the star Vega, though the object had been travelling for so long that Vega itself had moved significantly from its position when the journey began. The calculations revealed a visitor that had been wandering interstellar space for hundreds of millions of years, a cosmic nomad older than the dinosaurs. 3I. Atlas presents similar mathematical puzzles. Its trajectory suggests origins in the thick disk of our galaxy, that population of older stars that formed when the Milky Way was young. The object's journey to our solar system likely began billions of years ago, making it a relic from the early epochs of galactic evolution. The challenge of intercepting such objects lies in the enormous speeds involved. ʻOumuamua was travelling at about 26 kilometers per second relative to the Sun when it passed through our system. 3I. Atlas moves somewhat more slowly, but still at velocities that dwarf anything achieved by human spacecraft. For comparison, the fastest human-made object, the Parker Solar Probe, reaches maximum speeds of about 200 kilometers per second during its closest approaches to the Sun, but only in brief moments when boosted by solar gravity. To intercept an interstellar object, a spacecraft must match not only its speed, but also its direction of travel. This requires what engineers call delta V, the change in velocity needed to alter a spacecraft's trajectory. The delta V requirements for interstellar intercepts are enormous, far beyond the capabilities of most existing spacecraft. The proposed Juno flyby of 3I, Atlas, represents a clever workaround to these limitations. Rather than trying to match the comet's velocity, the mission would use Jupiter's massive gravity as a slingshot, timing Juno's trajectory to intersect the comet's path at high relative speed. The encounter would be brief, lasting only minutes, but it would provide humanity's first close-range look at an interstellar visitor. This technique, known as the Oberth effect, allows spacecraft to gain energy by firing their engines while deep in a gravitational well. The principle is similar to a runner gaining speed by running downhill. The same amount of engine thrust produces greater velocity change when applied in the presence of strong gravity. Ground-based observations of interstellar objects face their own technical challenges. These visitors are typically small, dark, and moving fast against the starfield, making them difficult targets for conventional telescopes. Their discovery often depends on automated sky surveys that can detect the subtle motion of faint objects against the background stars. Once detected, spectroscopic analysis becomes crucial for understanding the object's composition and behavior. Spectroscopy works by analyzing the wavelengths of light reflected or emitted by an object, creating a unique fingerprint that reveals the presence of specific atoms and molecules. For 3I, Atlas, this technique confirmed the presence of water vapor, carbon dioxide, and other molecules expected from a sublimating comet. But spectroscopy has limitations when applied to interstellar objects. The distances involved mean that signals are weak, requiring long exposure times and sophisticated instruments. The object's rapid motion across the sky further complicates observations, as telescopes must track them precisely while gathering light over extended periods. Radio astronomy offers another window into the nature of these visitors. Radio telescopes can detect natural emissions from the interaction between charged particles and magnetic fields, providing information about the object's internal structure and composition. They can also search for artificial signals that might indicate technological origins. The search for artificial signals from interstellar objects involves sophisticated signal processing techniques. Astronomers look for narrow-band emissions, repetitive patterns, or modulated signals that might indicate intelligent origin. So far, no such signals have been detected from either ʻOumuamua or 3I, Atlas, but the search continues as our instruments become more sensitive. Gravitational effects provide another tool for studying these objects. As interstellar visitors pass near massive bodies like the Sun or Jupiter, their trajectories bend according to Einstein's theory of general relativity. By precisely measuring these deflections, astronomers can infer information about the object's mass and internal structure. The acceleration anomaly observed in ʻOumuamua's trajectory exemplifies how precise measurements can reveal unexpected behavior. The deviation from a purely gravitational path was tiny, measurable only through careful analysis of multiple observations over time. Such precision requires extraordinary care in data collection and analysis, accounting for all possible sources of error and bias. Future missions to study interstellar objects will likely employ more advanced techniques. Dedicated intercept spacecraft could be designed with the enormous delta-v capabilities needed to match velocities with these high-speed visitors. Such missions might deploy multiple probes to study different aspects of the target object, creating a comprehensive picture of its structure and behavior. Alternatively, we might develop fast response missions capable of launching quickly when new interstellar objects are detected. These would require new technologies for rapid spacecraft assembly and launch, possibly using pre-positioned components that could be quickly configured for specific mission requirements. The technical challenges of studying interstellar objects reflect the broader difficulty of exploring space beyond our solar system. The vast distances, enormous speeds, and limited observation windows push our current capabilities to their limits. Yet each successful observation, each new technique developed, each careful analysis brings us closer to understanding these mysterious visitors. As you contemplate the elegant physics underlying these cosmic encounters, consider how the same mathematical principles that describe the motion of interstellar objects also govern the trajectories of spacecraft, the orbits of planets, and the paths of stars through the galaxy. The universe operates according to comprehensible laws, yet those laws permit phenomena that challenge our imagination and push the boundaries of the possible. Whether ʻOumuamua and 3I, Atlas, are natural wanderers or something more extraordinary, their presence in our solar system demonstrates the dynamic, interconnected nature of the galaxy we call home. Each technical measurement, each careful calculation, each precise observation adds to our understanding of both these specific objects and the broader cosmos they represent. Part 8. Historical and Cultural Context. Human History of Looking Outward. Since humanity first gazed upward at the night sky, we have been storytellers of the cosmos. Long before we understood the true nature of celestial objects, our ancestors watched the heavens and wove the movements of stars, planets, and comets into the fabric of human culture. The appearance of unexpected visitors in the sky has always carried special significance, marking moments of wonder, fear, and transformation in human societies around the world. Ancient civilizations tracked what they called guest stars and hairy stars, objects that appeared suddenly in familiar constellations or moved against the steady background of the celestial sphere. Chinese astronomers meticulously recorded these phenomena, creating detailed chronicles that modern scientists still consult when studying historical supernovae and comet appearances. The Babylonians developed sophisticated mathematical models to predict the movements of planets, while ancient Greek philosophers debated whether these wandering lights were gods, distant suns, or something else entirely. Comets held particular fascination and terror for our ancestors. Unlike the predictable motions of planets and stars, comets appeared without warning, blazed across the sky for weeks or months, then vanished as mysteriously as they had arrived. Medieval European chronicles described them as omens of disaster, harbingers of plague, war, or the death of kings. The appearance of what we now know as Halley's Comet in 1066 was recorded in the Bayeux Tapestry as a portent of the Norman conquest of England. Yet even in these early interpretations, we can see the seeds of modern scientific thinking. Chinese astronomers classified different types of comets based on their appearance and behavior, noting that some returned at regular intervals while others appeared only once. Islamic scholars during the medieval period built upon Greek and Persian astronomical traditions, developing more sophisticated models for celestial mechanics that would later influence European Renaissance thinking. The transformation from mythological to scientific understanding accelerated during the scientific revolution. Galilei's telescopic observations of Jupiter's moons demonstrated that not all celestial bodies orbited Earth, challenging fundamental assumptions about our place in the cosmos. His contemporary Johannes Kepler worked out the mathematical laws governing planetary motion, showing that the same physical principles operating on Earth also governed the movements of distant worlds. Perhaps most relevant to our current story, Edmund Halley applied Newton's new theory of gravity to predict the return of the comet that now bears his name. By calculating backward from historical observations, Halley demonstrated that comet sightings in 1531, 1607, and 1682 were actually the same object returning on a predictable orbit. His successful prediction of the comet's return in 1758 marked a triumph of mathematical astronomy and helped establish the scientific method as a reliable tool for understanding natural phenomena. The 19th and early 20th centuries brought increasingly sophisticated observations of comets and asteroids. Photographers began creating permanent records of celestial visitors, while spectroscopy revealed the chemical composition of objects millions of kilometers away. These advances laid the groundwork for modern planetary science and our current understanding of solar system formation and evolution. The space age brought humanity's first direct encounters with these ancient wanderers. Robot spacecraft like Giotto flew through the coma of Halley's Comet in 1986, transmitting back the first close-up images of a comet's nucleus. Subsequent missions landed on asteroids, collected samples from comet tails, and even crashed deliberately into comet nuclei to study their composition. Each mission revealed new complexities in these apparently simple chunks of ice and rock. Parallel to our growing understanding of comets and asteroids, the 20th century saw the emergence of serious scientific interest in the possibility of extraterrestrial intelligence. The development of radio astronomy opened new possibilities for detecting artificial signals from distant civilizations. Projects like SETI, Search for Extraterrestrial Intelligence, began systematically listening to the cosmos, searching for patterns in radio noise that might indicate intelligent origin. Frank Drake's famous equation, formulated in 1961, attempted to estimate the number of communicating extraterrestrial civilizations in our galaxy. While the uncertainties in Drake's equation are enormous, it focused scientific attention on the possibility that intelligence might be common in the universe. This shift in thinking prepared the ground for serious consideration of artificial explanations for unusual astronomical phenomena. The space program itself became humanity's first attempt to send messages to potential extraterrestrial observers. The Pioneer 10 and 11 spacecraft, launched in the early 1972, carried golden plaques designed to communicate basic information about humanity to any intelligent beings who might encounter them. The Voyager spacecraft went further, carrying golden records containing sounds and images from Earth. These missions made humanity itself an interstellar civilization, at least in a small way. Our spacecraft are now wandering the galaxy, much as ʻOumuamua and 3I, Atlas, wander through our solar system. From the perspective of any alien civilization that discovers them, Pioneer and Voyager might appear as mysterious visitors carrying cryptic messages about their origin and purpose. This historical perspective provides crucial context for understanding our current reaction to interstellar visitors. The human tendency to see patterns and meaning in celestial phenomena runs deep in our cultural DNA. When ʻOumuamua exhibited unusual characteristics, it was natural for some observers to speculate about artificial origins. The fact that such speculation now takes scientific rather than mythological form represents the evolution of human thinking, but the underlying psychological impulse remains unchanged. Science fiction has also played a crucial role in preparing human imagination for the possibility of contact with extraterrestrial intelligence. From H.G. Wells's War of the Worlds to Arthur C. Clarke's Childhood's End, from Carl Sagan's Contact to Liu Cixin's three-body trilogy, literature and film have explored countless scenarios for first contact. These stories shape public expectations about how such contact might occur and what it might mean for humanity's future. The recurring theme in many of these fictional works is the idea of gradual revelation. Rather than dramatic invasion or obvious contact, many authors have imagined first contact as a subtle process, beginning with ambiguous signals or mysterious visitors that could be interpreted as either natural phenomena or evidence of intelligence. This fictional template may influence how we interpret real astronomical discoveries, making us more likely to see potential artificial explanations in unusual observations. Popular culture has also been shaped by decades of UFO reports and government investigations. While most UFO sightings have conventional explanations, the phenomenon has created a cultural expectation that extraterrestrial visitors might already be present in our vicinity, observing us from a distance. This background of speculation and conspiracy theory can make it difficult to evaluate extraordinary claims about interstellar objects with appropriate scientific rigor. Yet history also shows us the importance of remaining open to genuinely revolutionary discoveries. The heliocentric solar system, continental drift, quantum mechanics, and relativity were all initially met with skepticism from established scientific authorities. Some of the most important advances in human knowledge have come from taking seriously observations that didn't fit conventional expectations. The challenge is distinguishing between genuinely anomalous phenomena that might indicate new physics or even extraterrestrial intelligence and more mundane explanations that simply haven't been considered yet. This requires a delicate balance between healthy skepticism and openness to extraordinary possibilities. As we continue to study ʻOumuamua, 3I, Atlas, and whatever other interstellar visitors the future may bring, we carry with us the accumulated wisdom of thousands of years of watching the skies. Our ancestors saw gods and omens in unexpected celestial visitors. We see physics and chemistry, orbital mechanics and spectroscopy. Yet perhaps we also see something of the same wonder and curiosity that drove ancient astronomers to map the movements of the stars. In the gentle transition from day to night, as the first stars appear in the deepening sky, we continue humanity's oldest tradition, looking outward with wonder, seeking to understand our place in the vast cosmos that surrounds us. Whether our current interstellar visitors prove to be natural wanderers or something more extraordinary, they remind us that the universe still holds surprises for those patient enough to watch and wise enough to wonder. Part 9. Psychological and Social Dimensions. Why we yearn for cosmic contact. In the deepest hours of night, when the everyday concerns of human life fade into the background, many of us find ourselves contemplating our place in the vast cosmos. There's something profound about standing under a star-filled sky, feeling simultaneously humbled by the universe's immensity and curious about what might exist in those distant points of light. This yearning for cosmic connection runs deeper than mere scientific curiosity. It touches something fundamental about human nature and our need to understand our place in existence. The psychological appeal of believing we're not alone in the universe speaks to one of humanity's most persistent anxieties: cosmic loneliness. Earth appears to be a tiny oasis of life in an incomprehensibly vast and seemingly empty universe. The silence we encounter when we listen to the stars can feel oppressive, suggesting that we might be the only conscious beings in a cosmos that stretches beyond our ability to imagine. This existential loneliness has practical implications for how we interpret ambiguous phenomena like ʻOumuamua and 3I, Atlas. When faced with unusual observations that could have either natural or artificial explanations, our deep desire for companionship in the cosmos may unconsciously bias us toward the more exciting interpretation. The possibility that we're being visited by intelligent observers offers a kind of cosmic comfort, a reassurance that consciousness and curiosity exist elsewhere in the universe. Curiosity itself represents one of humanity's most distinctive and valuable traits. Our species has succeeded in part because we're driven to explore, to question, to push beyond the boundaries of the known. This trait served our ancestors well when they ventured out of Africa to populate the globe, and it drives our current exploration of space and the fundamental nature of reality. When we encounter something genuinely mysterious, like an interstellar visitor with unusual characteristics, our curiosity naturally seeks the most interesting possible explanation. The idea that ʻOumuamua might be an alien probe satisfies our need for discovery and wonder in ways that a more conventional explanation cannot. Even if the evidence doesn't strongly support artificial origins, the possibility alone provides a kind of intellectual excitement that makes the mystery more engaging. Yet curiosity is paired with its psychological counterpart, fear of the unknown. The same openness that makes us yearn for contact with extraterrestrial intelligence also makes us anxious about what such contact might bring. Science fiction has provided countless scenarios where first contact leads to human extinction, slavery, or cultural dissolution. These fictional warnings tap into deep-seated fears about encounters with superior powers. This fear creates a complex psychological dynamic around interstellar visitors. Part of us wants them to be artificial, to represent contact with cosmic intelligence. Another part of us fears what such contact might mean for humanity's independence and future. We simultaneously hope for and dread confirmation that we're being observed by advanced civilizations. The media landscape shapes these psychological responses in powerful ways. Decades of science fiction films and television shows have created cultural templates for how extraterrestrial contact might occur. From the benevolent visitors in Close Encounters of the Third Kind to the destructive invaders of Independence Day, popular entertainment has provided a range of scenarios that influence public expectations about alien contact. These fictional templates can affect how we interpret real astronomical discoveries. When ʻOumuamua exhibited acceleration that couldn't be easily explained by conventional physics, it was natural for many people to immediately think of spacecraft propulsion systems. The unusual shape inferred from its light curve reminded observers of the elongated alien vessels common in science fiction. Even serious scientists found themselves using analogies to fictional spacecraft when discussing possible artificial explanations. The internet and social media have amplified these psychological dynamics, creating echo chambers where speculation can rapidly evolve into apparent certainty. Initial suggestions that an interstellar object might have artificial origins can be shared, elaborated, and reinforced across online communities faster than scientific analysis can provide definitive answers. This creates a kind of parallel narrative that exists alongside the scientific investigation, sometimes influencing how the evidence is interpreted. Human pattern recognition, while generally adaptive, can also lead us astray when dealing with rare phenomena. We're evolutionarily predisposed to see agency and intention in ambiguous situations because assuming predators or competitors were present often meant the difference between survival and death. This same tendency can make us more likely to interpret unusual astronomical observations as evidence of intelligence rather than natural processes. The small sample size of interstellar visitors compounds this problem. With only 3 confirmed objects of this type, we lack the statistical foundation needed to determine what's normal and what's anomalous. Each new discovery carries disproportionate weight in shaping our understanding, making it easy to overinterpret limited data. Religious and spiritual perspectives add another layer of complexity to public reactions to potential extraterrestrial contact. Some traditions embrace the possibility of life throughout the cosmos as evidence of divine creativity and abundance. Others find the idea threatening to human-centered theological frameworks. These varying perspectives influence how different communities interpret and respond to claims about artificial interstellar objects. The scientific community itself struggles with these psychological dynamics. Scientists are trained to maintain objectivity and follow evidence wherever it leads, but they're also human beings subject to the same cognitive biases and emotional responses as everyone else. The tension between professional skepticism and personal curiosity can create internal conflicts when dealing with genuinely anomalous observations. There's also a social dimension to how scientists approach extraordinary claims. The peer review process that ensures scientific rigor can also create pressure to conform to conventional explanations. Researchers who propose artificial explanations for astronomical phenomena risk damaging their professional reputations if they're wrong, creating an asymmetric incentive structure that favors conservative interpretations. Yet this conservative bias serves an important function in maintaining scientific credibility. The history of science is filled with extraordinary claims that turned out to have mundane explanations. Pulsars were initially thought to be signals from extraterrestrial civilizations before being identified as rotating neutron stars. The famous canals of Mars turned out to be optical illusions rather than evidence of Martian engineering. Most UFO sightings have conventional explanations involving atmospheric phenomena, aircraft, or astronomical objects. The challenge is maintaining appropriate skepticism while remaining open to genuinely revolutionary discoveries. This requires a kind of psychological flexibility that can hold multiple possibilities in mind simultaneously without prematurely committing to any particular explanation. It means being comfortable with uncertainty and ambiguity, qualities that don't come naturally to most people. The potential social impact of confirmed extraterrestrial contact adds stakes to these discussions that go far beyond academic interest. Such confirmation would represent one of the most significant discoveries in human history, fundamentally changing our understanding of our place in the universe. It might unite humanity around our shared cosmic significance, or it might create new divisions between those who see such contact as opportunity and those who view it as a threat. These high stakes can unconsciously influence how we evaluate evidence about potential artificial visitors. Those who believe such contact would be beneficial for humanity might be more willing to accept artificial explanations for ambiguous phenomena. Those who fear the consequences of contact might be more inclined to dismiss such possibilities or avoid investigating them seriously. As you settle into the quiet contemplation that precedes sleep, consider how these psychological and social dynamics shape our relationship with the mystery of interstellar visitors. Our responses to ʻOumuamua and 3I, Atlas, reveal as much about human nature as they do about the objects themselves. We are creatures caught between wonder and fear, curiosity and caution, hope and anxiety about what we might discover when we look up at the stars. The cosmos may indeed be stranger than we imagine, filled with intelligence and purpose we're only beginning to detect. Or it may be exactly as it appears, vast, ancient, and largely empty, with life and consciousness representing rare and precious exceptions to the general rule of lifeless matter and energy. Either possibility carries profound implications for how we understand ourselves and our future among the stars. In the end, our yearning for cosmic contact reflects something beautiful about human nature, our refusal to accept isolation, our determination to reach beyond ourselves, our hope that consciousness and curiosity exist throughout the universe. Whether or not we find the companions we seek among the stars, the search itself ennobles us and connects us to the greatest questions that face any intelligent species fortunate enough to wonder about its place in the cosmos. Part 10. Counterpoints. Grounded views. Organic comet. No ET required. As the night deepens and our exploration of cosmic possibilities continues, it's essential to ground our wandering thoughts in the solid foundation of mainstream scientific understanding. While speculation about artificial interstellar visitors captures the imagination, the weight of evidence supports a more conventional but no less remarkable explanation. 3I. Atlas appears to be exactly what most astronomers believe it to be, an ancient comet from interstellar space, following natural laws as it journeys through our solar system. The spectroscopic evidence for 3I, Atlas's natural composition, is compelling and consistent. Multiple independent observations by space-based telescopes have detected water vapor, carbon dioxide, carbon monoxide, and other molecules streaming from the object as it approaches the sunday. These emissions match theoretical predictions for how a primordial comet should behave when heated by solar radiation after millions of years in the frozen depths of interstellar space. The Hubble Space Telescope's detailed observations show a classic comet structure, a nucleus surrounded by a coma of gas and dust, with material streaming away to form the characteristic tail. The brightness variations and spectral signatures follow well-established patterns that have been observed in thousands of other comets throughout the solar system. If 3I Atlas were an artificial object disguised as a comet, the creators would have had to replicate these complex physical and chemical processes with extraordinary precision. The James Webb Space Telescope's infrared observations have provided unprecedented detail about the object's composition and behavior. The telescope's sophisticated instruments can detect subtle differences in molecular emissions that would be difficult to fake convincingly. The data shows isotopic ratios and chemical abundances consistent with material formed in the cold outer regions of a stellar system billions of years ago. Regarding the seemingly suspicious orbital alignment with our solar system's ecliptic plane, statisticians and orbital dynamicists offer more prosaic explanations. While the probability of any single interstellar object arriving on such a trajectory is indeed low, the universe contains countless such objects following every conceivable path through space. When dealing with rare phenomena observed over short time periods, apparently improbable events become not only possible but inevitable. Consider the anthropic selection effect at work in our observations. We're more likely to detect interstellar objects that pass relatively close to Earth and the Sun, where they become bright enough for our telescopes to spot. Objects following trajectories that take them through the inner solar system, where planetary heating makes them more visible, are naturally overrepresented in our sample. 3. Atlas's ecliptic alignment may simply reflect this observational bias rather than any artificial intent. The timing of 3I, Atlas's arrival, following so closely after ʻOumuamua, also has natural explanations. The development of more sophisticated sky surveys in recent years has dramatically increased our ability to detect these rare visitors. Projects like Atlas, Linear, and Catalina Sky Survey scan larger areas of sky more frequently and with greater sensitivity than previous generations of telescopes. We may simply be entering an era where our technology has finally reached the threshold needed to routinely detect interstellar objects. Furthermore, computer models of galactic dynamics suggest that interstellar object encounters might not be as uniformly distributed in time as early estimates suggested. Gravitational interactions with nearby stars, encounters with molecular clouds, and the solar system's motion through different regions of the galaxy could create periods when such visits are more or less likely. We might be passing through a region of space with a higher density of interstellar debris, or our improved detection capabilities might be revealing a population that was always there but previously invisible to us. The apparent acceleration anomaly that made ʻOumuamua so intriguing has been reanalyzed multiple times since its discovery. While the deviation from a purely gravitational trajectory remains real, most astronomers now favor outgassing as the most likely explanation. Even very small amounts of material ejected from the object's surface can create measurable acceleration, especially for an object with ʻOumuamua's unusual geometry and low mass. Subsequent studies have shown that many of ʻOumuamua's apparently anomalous characteristics can be explained by natural processes operating under the extreme conditions of interstellar space. Its elongated shape might result from tidal disruption during a close encounter with a star millions of years ago. Its lack of visible coma could be explained by the depletion of volatile materials during its long journey through the galaxy, leaving behind a residue of refractory compounds that sublimate only slowly when heated. The scientific method itself provides powerful tools for distinguishing between natural and artificial explanations. Extraordinary claims require extraordinary evidence, not because scientists are close-minded, but because history shows that most unusual observations have conventional explanations once all the relevant physics is considered. Pulsars, initially nicknamed LGM, Little Green Men, because of their regular radio pulses, turned out to be rapidly rotating neutron stars. Tabby's star, which dimmed mysteriously and sparked speculation about alien megastructures, appears to be surrounded by unusual dust clouds. The burden of proof for artificial explanations remains high because the implications would be so profound. Confirming that even one interstellar visitor was of artificial origin would revolutionize our understanding of the galaxy and our place within it. Such a claim demands multiple independent lines of evidence, reproducible observations, and the elimination of all plausible natural alternatives. Current observations of 3I, Atlas, fall far short of meeting this standard. While the object's orbital alignment is statistically unlikely, it's not impossible. While the timing of its arrival after ʻOumuamua seems suspicious, it's not inexplicable. While its behavior as it approaches the Sun is interesting, it's entirely consistent with a natural comet following well-understood physical laws. Radio telescope searches for artificial signals from both ʻOumuamua and 3I, Atlas, have found nothing unusual. These observations covered a wide range of frequencies and employed sensitive techniques capable of detecting even weak transmissions. If these objects were artificial probes maintaining communication with their creators, we might expect to detect at least some evidence of such signals. The absence of detectable artificial emissions doesn't definitively prove these objects are natural, but it's consistent with that explanation. An advanced civilization might use communication methods beyond our current understanding, but the complete absence of any anomalous radio emissions suggests that exotic explanations may be unnecessary. Professional astronomers studying these objects bring decades of experience in distinguishing between natural and artificial phenomena. They understand the subtle signatures that might indicate technological origin and know what to look for in their data. The fact that the overwhelming majority of experts who have studied ʻOumuamua and 3I, Atlas, conclude they are natural objects carries significant weight in the scientific evaluation of these phenomena. This doesn't mean that all questions have been answered or that artificial explanations should be dismissed without consideration. Science advances by maintaining openness to unexpected discoveries while requiring rigorous evidence before accepting revolutionary claims. The careful study of interstellar visitors represents exactly this kind of balanced approach. Thorough investigation of all possibilities guided by evidence rather than speculation. The natural explanation for these objects is itself profoundly interesting. 3I. Atlas represents a piece of another star system, formed billions of years ago in conditions we can only imagine. It carries with it a record of processes that occurred when our own solar system was young, preserved in the frozen depths of interstellar space like a message in a cosmic bottle. The isotopic ratios locked within its ice tell stories about the nuclear furnaces that created its constituent atoms. The organic compounds that may be present speak to the chemical complexity possible in interstellar environments. Even as a purely natural object, 3I, Atlas offers insights into stellar formation, planetary system evolution, and the distribution of materials throughout our galaxy. The rarity of interstellar visitors makes each one precious for advancing our understanding of the cosmos. Whether they arrive as scouts and motherships or as ancient wanderers, they provide direct samples of environments far beyond our reach. Future missions to study such objects could revolutionize our knowledge of how stars and planets form, how organic chemistry develops in space, and what conditions exist in the vast regions between stellar systems. The danger of premature commitment to extraordinary explanations lies not just in the possibility of being wrong, but in the way such commitments can narrow our investigation. If we decide too quickly that an object must be artificial, we might miss opportunities to learn about natural processes that could be equally fascinating and scientifically valuable. Conversely, if we reflexively dismiss all possibility of artificial origin, we might overlook genuine signs of extraterrestrial technology should they ever appear. The key is maintaining what scientists call strong opinions, weakly held, being willing to advocate for the interpretation best supported by current evidence while remaining ready to change course if new data demands it. The scientific process provides mechanisms for resolving such debates through continued observation and analysis. The proposed Juno flyby of 3I, Atlas, if it occurs, could provide definitive answers about the object's nature. Close-range observations might reveal surface features, internal structure, or other characteristics that would clearly distinguish between natural and artificial origins. Even if such missions confirm that our current interstellar visitors are natural objects, they will have served an important purpose in testing our ability to detect and study such phenomena. Future visitors might indeed prove to be artificial, and the techniques developed for studying ʻOumuamua and 3I, Atlas, will be essential for recognizing and understanding them. The healthy skepticism of the mainstream scientific community toward artificial explanations reflects hard-won wisdom about the need for rigorous evidence when making extraordinary claims. This skepticism isn't closed-mindedness, but rather a recognition that the universe consistently surprises us with natural phenomena more remarkable than our imaginations typically conceive. The history of astronomy is filled with discoveries that initially seemed to require exotic explanations, but ultimately yielded to more conventional understanding. Quasars were once thought to be relatively nearby objects with impossible energy outputs before being recognized as supermassive black holes at cosmological distances. Fast radio bursts puzzled astronomers for years before their origins began to be understood through patient observation and analysis. This pattern suggests that apparent anomalies in interstellar objects are more likely to be resolved through better understanding of natural processes than through confirmation of artificial origins. The universe operates according to comprehensible physical laws, and these laws typically provide adequate explanations for observed phenomena once all relevant factors are considered. Yet the very fact that we can seriously consider artificial explanations for interstellar visitors represents a remarkable achievement in human knowledge and capability. We've developed instruments sensitive enough to detect these rare travelers, mathematical techniques sophisticated enough to calculate their origins and destinations, and theoretical frameworks comprehensive enough to distinguish between natural and artificial possibilities. Whether ʻOumuamua and 3I, Atlas, proved to be cosmic wanderers or something more extraordinary, their study has advanced our understanding of interstellar space, improved our detection capabilities, and prepared us for whatever future discoveries await. The questions they've raised have stimulated new research, inspired technological developments, and captured public imagination in ways that purely theoretical studies might not have achieved. In the quiet contemplation of the night hours, as our minds settle into the rhythm of approaching sleep, we can appreciate both the wonder of natural cosmic processes and the remarkable human achievement represented by our ability to detect and study these distant visitors. The universe reveals its secrets gradually, rewarding patience, precision, and open-minded investigation. The mystery of interstellar objects reminds us that science is not about having all the answers, but about asking better questions and developing better tools for finding those answers. Whether the cosmos holds artificial intelligences traveling between the stars, or simply ancient chunks of ice and rock following gravitational laws across the void, our quest to understand these phenomena connects us to the deepest questions about existence, consciousness, and our place in the vast cosmic story. Part 11. Synthesis: Bridging Reality and Possibility. As we draw together the many threads of our cosmic investigation, the picture that emerges is one of remarkable complexity, where established scientific facts interweave with tantalizing possibilities, and where the boundary between the known and the unknown remains beautifully, mysteriously blurred. Let us first anchor ourselves in what we know with reasonable certainty. ʻOumuamua, discovered in 2017, was definitively the first confirmed interstellar object to visit our solar system. Its hyperbolic trajectory, unusual elongated shape, and slight but measurable acceleration created a genuine scientific puzzle that remains partially unsolved. The object's brief 11-day observation window left us with more questions than answers, but it undeniably proved that visitors from other star systems do occasionally grace our cosmic neighborhood. 3I, Atlas, detected in 2025, represents our third confirmed interstellar visitor and the most thoroughly studied such object to date. Its larger size, extended observation period, and obvious cometary activity have provided unprecedented insights into the nature of interstellar wanderers. Spectroscopic analysis confirms the presence of water vapor, carbon dioxide, and other molecules consistent with a natural comet, while its trajectory through the ecliptic plane and timing relative to Oumuamua's visit raise intriguing questions about coincidence versus intention. The scientific evidence, viewed through the lens of conventional physics and chemistry, strongly supports natural explanations for both objects. They appear to be ancient remnants of planetary system formation, blasted into interstellar space by gravitational interactions or catastrophic events millions or billions of years ago. Their compositions match theoretical predictions for such objects. Their behaviors follow understood physical laws, and their characteristics fall within the range of what we might expect from cosmic debris that has wandered the galaxy for eons. Yet the speculative threads we've explored cannot be easily dismissed as mere fantasy. The statistical improbability of 3I, Atlas's orbital alignment, the curious timing of these visits, and the lingering mysteries surrounding Oumuamua's acceleration create space for more extraordinary interpretations. The Scout and Mothership hypothesis, while unproven, provides a coherent framework that could potentially explain these apparent coincidences. The dark forest theory offers a sobering context for considering how advanced civilizations might conduct reconnaissance of other star systems. If the galaxy is indeed populated by intelligent species maintaining silence out of existential caution, then disguised probes following natural-seeming trajectories would represent a logical approach to gathering information about potential neighbors. The fact that such probes would be nearly indistinguishable from genuine interstellar debris makes this possibility both plausible and inherently difficult to verify or disprove. The scientific community's response to these speculations has been appropriately measured. While most researchers favor natural explanations based on current evidence, the door remains open to more extraordinary possibilities should compelling proof emerge. This balance between skepticism and openness represents the scientific method at its best. Rigorous evaluation of evidence combined with intellectual humility about the limits of current understanding. The proposed Juno flyby of 3I, Atlas, embodies this balanced approach. If executed, such a mission could provide definitive answers about the object's nature through close-range observations impossible from Earth. Whether it confirms the natural comet hypothesis or reveals something more extraordinary, the mission would represent a crucial step in our understanding of interstellar visitors. The cultural and psychological dimensions of this mystery reveal as much about humanity as about the objects themselves. Our yearning for cosmic companionship, our tendency to see patterns and agency in ambiguous phenomena, and our oscillation between wonder and fear when confronted with the unknown all influence how we interpret and respond to these discoveries. The very questions we ask about interstellar visitors reflect our deepest concerns about isolation, purpose, and our place in the cosmic order. The historical context provides perspective on our current situation. Humanity has always struggled to distinguish between natural phenomena and signs of intelligence or divine intervention when confronted with unexpected celestial events. Our scientific revolution represents a gradual shift toward explanations based on natural laws rather than supernatural agency, but the underlying human impulse to seek meaning and connection in cosmic events remains strong. The technical challenges of studying interstellar objects highlight both the remarkable achievements of modern astronomy and the limitations that constrain our investigations. Our ability to detect, track, and analyze these rare visitors across interstellar distances represents an extraordinary feat of human ingenuity and technological sophistication. Yet the brief observation windows, vast distances, and faint signals involved in such studies leave significant room for uncertainty and multiple interpretations. Looking toward the future, we can anticipate that additional interstellar visitors will be discovered as our detection capabilities continue to improve. Each new object will add to our understanding of these phenomena, gradually building a statistical foundation that may help distinguish between natural patterns and genuine anomalies. The development of faster response missions capable of intercepting newly discovered objects could revolutionize our ability to study them in detail. The possibility that we might someday confirm artificial origin for an interstellar visitor carries profound implications for humanity's future. Such a discovery would represent one of the most significant events in human history, fundamentally altering our understanding of our place in the universe and our relationship with potential cosmic neighbors. The social, philosophical, and practical consequences of confirmed extraterrestrial contact would ripple through every aspect of human civilization. Yet, even if all interstellar visitors prove to be natural objects, their study will continue to advance our knowledge of galactic chemistry, stellar system formation, and the distribution of materials throughout space. Each wandering chunk of ancient ice and rock carries within it a record of conditions and processes that occurred billions of years ago in star systems we may never directly observe. They are time capsules from the early universe, messengers bearing news from distant shores we can barely imagine. The synthesis of scientific rigor and speculative wonder that characterizes our investigation of these objects reflects something essential about the human spirit. We are creatures capable of both careful analysis and bold imagination, of respecting evidence while remaining open to possibilities that challenge our preconceptions. This duality serves us well as we navigate between the twin dangers of closed-minded skepticism and credulous acceptance. In the end, perhaps the most important insight from our exploration of interstellar visitors is that the universe consistently proves to be stranger, more complex, and more wonderful than our theories predict. Whether ʻOumuamua and 3I, Atlas, are natural wanderers or something more purposeful, their presence in our solar system reminds us that cosmic surprises await those patient enough to watch the skies and wise enough to recognize significance when it appears. As we prepare to conclude our nocturnal journey through these cosmic mysteries, we're left with a sense of vast possibilities stretching out before us like the star-filled darkness beyond our atmosphere. The questions raised by our interstellar visitors may take decades to resolve, but the search for answers will undoubtedly lead us to discoveries and insights we cannot yet imagine. The cosmos is calling, and whether the voice belongs to ancient physics or alien intelligence, our response remains the same. We listen, we wonder, and we continue reaching toward understanding across the infinite dark that separates us from the stars. Part 12. Conclusion. The Eternal Mystery of the Stars. As the final moments of our nocturnal exploration drift past like cosmic dust in the solar wind, we return to the question that began our journey. Could ʻOumuamua have been merely a scout, with 3I, Atlas, following as something larger and more purposeful? The answer, like so much in the vast universe around us, remains beautifully, mysteriously uncertain. We have travelled together through the technical details of orbital mechanics and spectroscopy, through the psychological landscapes of human longing and fear, through speculative frameworks that stretch our imagination while remaining grounded in the possible. We have weighed evidence and examined alternatives, considered both the extraordinary and the mundane, and found ourselves arriving at a place of informed wonder rather than definitive conclusion. This uncertainty is not a failure of our investigation, but rather its greatest success. The universe has presented us with phenomena that challenge our current understanding while respecting the boundaries of scientific method. Whether these interstellar visitors are ancient wanderers shaped by natural forces or something more deliberate and purposeful, they have succeeded in expanding our conception of what is possible in the cosmos we inhabit. Think for a moment about how little we truly know of the galaxy's visitors. In the vast ocean of space that surrounds us, countless objects drift on journeys that began before our solar system formed. Some may be fragments blasted from distant worlds by catastrophic impacts. Others might be the last remnants of planets whose stars have long since died. And perhaps, just perhaps, a few might be the creations of minds we have never imagined, carrying purposes we are only beginning to contemplate. Our ancient ancestors watched the same stars that wheel overhead tonight, but they could never have conceived of the true distances involved, the billions of years these lights have been burning, or the possibility that travelers from such distant shores might occasionally visit our cosmic neighborhood. We have gained knowledge they could never possess, yet we find ourselves still asking the same fundamental questions. Are we alone? What lies beyond our immediate reach? What purpose, if any, guides the movements of objects through the cosmic deep? The parallel between those ancient sky watchers and ourselves speaks to something enduring in human nature. We are a species that looks up, that wonders, that refuses to accept easy answers when deeper mysteries beckon. The same curiosity that led our predecessors to map the movements of planets and predict the return of comets now drives us to build ever more sensitive instruments, to launch spacecraft across interplanetary distances, and to listen for signals that might carry news from civilizations we have never met. 3. Atlas continues its journey through our solar system as we speak, following the ancient laws of gravity and momentum that govern all motion in the cosmic void. Whether it carries within its icy nucleus the instruments of distant observers, or simply the chemical legacy of stellar processes that occurred billions of years ago, it represents a connection to realms far beyond our earthly experience. In a few months, it will pass its closest approach to the Sun, perhaps revealing new details about its composition and behavior, then begin the long journey back to the darkness between the stars. By the time it crosses the outer boundary of our solar system, decades hence, most of us who have wondered about its nature will have returned to the dust from which we came. But our questions will persist, carried forward by new generations who will train new instruments on new visitors, each discovery building upon the foundation of knowledge we have established. The beauty of unanswered mysteries lies not in their ultimate resolution, but in their capacity to inspire continued exploration. The questions raised by our interstellar visitors have already stimulated advances in detection technology, prompted new theoretical frameworks, and captured the imagination of millions who might never have contemplated the possibility of travelers from other star systems. Whether these objects prove to be natural or artificial, they have served as catalysts for human curiosity and technological advancement. Future generations may indeed learn the truth about ʻOumuamua and 3I, Atlas. They may develop propulsion systems capable of catching up with these high-speed visitors for detailed examination. They may detect unambiguous signals from other star systems that provide context for understanding interstellar phenomena. They may even make direct contact with civilizations that have been observing us from afar, learning the true purpose behind any reconnaissance missions that might have visited our solar system. Or they may discover that the universe is exactly as it appears to most current observers, vast, ancient and largely empty, with islands of complexity, like our own solar system, representing rare exceptions to the general rule of lifeless matter, following physical laws across cosmic distances. Such a discovery would be no less profound than confirmation of extraterrestrial intelligence, for it would establish our own existence as something precious and improbable in a universe that had no obligation to create consciousness at all. Either way, the search itself ennobles us. The careful observation of interstellar visitors, the patient analysis of their behavior, the thoughtful consideration of alternative explanations, and the rigorous testing of hypotheses all contribute to the grand human project of understanding our place in existence. We are creatures who ask questions that may take centuries to answer, who build instruments to detect phenomena we can barely imagine, who launch messages into the void, hoping that someone, somewhere, might be listening. As you allow your mind to settle into the gentle rhythms that precede sleep, imagine 3i, Atlas, following its ancient trajectory through the star-filled darkness that surrounds us. Picture it as it appeared billions of years ago when it first began its journey, perhaps orbiting a star that has since exhausted its nuclear fuel and collapsed into a white dwarf. Consider the eons it spent in the cold emptiness between stellar systems, a silent traveller carrying within its frozen structure a record of conditions and processes that occurred when the universe itself was young. Whether it observes us with hidden instruments as it passes, whether it transmits our location and characteristics to distant recipients, whether it represents first contact conducted according to protocols we do not yet understand, we cannot say. But we can appreciate the remarkable circumstance that brought us together, a species that has learned to ask questions about the cosmos, and a visitor that has travelled unimaginable distances to provide us with an opportunity to seek answers. Curiosity, we have learned, is part of being human. It drives us to explore not just the geography of our own planet, but the vast territories of space and time that extend far beyond our physical reach. It compels us to build telescopes and spacecraft, to develop mathematical tools for understanding orbital mechanics, to create theoretical frameworks for distinguishing between natural phenomena and artificial intelligence. It connects us across generations and cultures in a shared quest for knowledge and understanding. The cosmos, as we have discovered tonight, is vast enough to contain endless stories. Whether those stories include chapters written by intelligences other than our own remains to be seen. But the very fact that we can wonder about such possibilities, that we can detect and study visitors from interstellar space, that we can imagine scenarios where scout ships precede motherships across the galaxy, speaks to something remarkable about the universe's capacity to create beings capable of contemplating their own existence. Let your thoughts drift now like cosmic dust carried on the solar wind, settling into the peaceful darkness that surrounds our small world. Tomorrow will bring new observations, new analyses, new opportunities to expand our understanding of the mysteries that visit us from the deep. Tonight belongs to wonder, to the quiet satisfaction of questions well asked, to the ancient human pleasure of looking up at the stars and knowing that we are part of something far grander than ourselves. The eternal mystery of the stars continues, as it has for billions of years before us, and as it will for billions of years after we are gone. We are privileged to participate in this cosmic story for the brief time that consciousness flickers within us, to add our own small contributions to humanity's growing understanding of the universe we inhabit. And somewhere in the darkness beyond our atmosphere, the cosmos keeps its secrets, waiting patiently for the day when we might finally be ready to learn the truth about the visitors who pass through our neighborhood, carrying with them messages from distant shores we can barely imagine. Sleep well, fellow travelers. The stars will keep their watch until morning comes again.